Welcome back. So next we want to talk about potential energy and a way of expressing the potential energy that can be generated by an electric field. The electric potential, which we often call voltage. But before we do that, we want to look at another nice application of Gauss's law. In the picture shown here, we have two conducting spheres that have an equal amount of charge. The charges will distribute evenly over the surface because the spheres are conducting, and we're asked, how does the electric field at A and B compare when A and B are 2 points that are the same distance from the center of each sphere? At first look, we can probably see that the electric field is pointing straight up in both of these cases. There will be an equal amount of charge to the right and to the left of the point we are trying to find the field for. So those components of the electric field will cancel each other out, and the field will point straight up. But which is stronger? Well, sphere A has some positive charge that is very close to point A. However, there's also a lot of positive charge that is quite far from point A. In point B, the charges look a bit more like a point charge, but still, how can we tell the difference? Well, if this was a calculus-based course, we would integrate the distances from the charges to A, which will work, but this is a bit of a brute force approach. So in fact, when I took Physics 2, however many years ago, that's mostly what I remember. We would be given all sorts of interesting shapes, and then that had charge distributed over them, and we would try and figure out the electric field generated by them using calculus. It was pretty interesting, but in this case, there's a more elegant, simpler strategy. We can use Gauss's law. In this case, we will want to draw a Gaussian surface around the two spheres, and it makes sense to draw the surface as a sphere around the center of the smaller sphere. We do this for both spheres, and we see that both spheres are exactly the same size, and the amount of charge inside of both spheres is exactly the same. If the spheres are the same size, then the surface area of each sphere must be the same, 4 pi r squared, so that means that if we want to find the flux going through the two spheres, well, we know that flux is the electric field times the area, and it is equal to the charge inside divided by epsilon naught. So the area of both spheres is exactly the same, and the amount of charge inside of both spheres is exactly the same, and epsilon naught is a universal constant, so that doesn't change either. So using Gauss's law, we've shown that the electric field at the 2 points here are identical. This is quite useful because we've talked about point charges quite a bit, but there aren't really any point charges. I guess you could say electron or protons, but in most cases charges are spread out over space. This shows that whenever you have a charged sphere, we can treat the charged sphere as if it is a point charge at the center of the sphere. Doing this proof with calculus is a bit more involved, but with Gauss's law, this is a very simple proof. This also shows that Gauss's law is quite powerful for solving problems, although the trick is usually you need to find out the right shape to use for your Gaussian surface. If you can do that, you can often get an intuitive solution to the electric field. Okay, so you have a quick problem to do here, and then we're going to start to review potential energy.